This video will cover section 8.4, multiplicative inverses and matrices and matrix equations. The first slide contains an introduction, and it is based on a very real story you might be familiar with, World War II. So, Andrew, could you please read it?
Yes.
Thank you.
In 1939, Britain's Secret Service hired top chess players, mathematicians, and other masters of logic to break the code used by the Nazis in communications between headquarters and troops. The project, which employed over 10,000 people, broke the code less than a year later, providing the Allies with information about Nazi troop movements throughout World War II. Messages must often be sent in such a way that the real meaning is hidden from everyone but the sender and the recipient. In this section, we will look at the role that matrices and their inverses play in this process.
Yeah. Okay, so just to expand a little bit on that story, that is true. They hire a lot of those very intelligent mathematicians, and also the crossword puzzle people that were interested in solving those. And so that's the way that they were able to decode the secret messages that the Nazis were sending through the radio, because they were coded using cryptography. Just to give you a very brief idea, and that's the movie that I was talking about, Imitation Game. Yes. And that's how the World War II ended, because thanks to math, actually. So for those of you who think math is not useful. So let's go to the last slide, very last one, so you can get an idea of what I'm talking about. Okay, so to encode a message, we have the alphabet here, and so we assign a number to each letter. And we're going to start just with a little one, an easy one. So if this one is going to be the word map. Now, sometimes you can write your matrix horizontally or vertically. The book chooses to do it vertically, so we're just going to keep that pattern. So for M, we have the letter 13. For A, we have the number 1, of course. T is 20. And then H is
8.
8. Thank you. Okay, so that will be the message before it is encoded, okay? So we'll call this original message. Then we're going to multiply it by the coding matrix, which is also called the key. Very good.
Yeah.
Yes. Yeah. So then, to encode the message, we're going to multiply. So we will multiply first row times first column. So -2 times 13, that will be -26. -3 times 1 is -3. And then we move on to first row, second column. So that will be -2 times 20, that's -40. And then -3 times 8 is
-24.
Thank you. Okay, then we move on to second row, first column. So 3 times 13, 39.
Yes.
4 times 1, 4. And then second row, second column. So 3 times 20, 60. 4 times 8. What is that?
32.
Thank you. Okay. So then we end this with -29, -64.
Miss.
Yeah, what? Can I make a mistake? Okay. 39 plus 3 is 33. No, I'm sorry. 43. And then 60 plus 32 is 92. Okay, so that will be the encoded message. So if I wanted to send a secret message to Matthew, I will send him that. Then Matthew will receive that, and to decode the message, Matthew will have to undo what I did. And so how do you undo multiplication?
Divided.
You divide, right? But we do not have division with matrices. So that is why we're going to need to multiply by its inverse, by its multiplicative inverse. And in a sense, it's the exact same thing as what we do with numbers, because let's say you have an equation such as 4x equals 16, and you want to solve for x. So you don't know you divide by 4, correct? Yes? Like you do that because you want to have just x by itself, or 1x. So, but what you are doing, in fact, is you are multiplying by the multiplicative inverse of 4, and that is 1 over 4. Remember, dividing by 4 is the same as multiplying by 1 over 4. And so once you do that, you will have here 4 over 4x, which equals 16 over 4. And of course, right here, what you're trying to get is just 1x, the identity. So we're going to be using those two words a lot, identity. The multiplicative identity for all real numbers is 1. Because if you have any number and you multiply it by 1, you get the same number. Whether the number is positive or negative or a fraction. So that is the identity. Now the other thing to consider is what I just went over here. The multiplicative inverse of real numbers. And for those, we could also summarize it as the reciprocal of it. So if you have a fraction like 7 over 5, the multiplicative inverse is going to be 5 over 7. And if you multiply them, you get 1, which is the identity. So that concept, it translates into matrices. And in section 8.3, we talked about the zero matrix, which is just a matrix with zeros inside all the entries. That was the additive inverse. But now the multiplicative identity for matrices is the one that looks like this. By the way, this one only applies to square matrices. Only square matrices. That means that we have the same number of rows and columns. And so the multiplicative identity of order n, this means the dimension is n, is a matrix with n rows and n columns the main diagonal, which is this one here, from the top left corner to the bottom right corner, the main diagonal consists of ones and zeros above and below or elsewhere. So we have a identity of order 2, a 2 by 2, an identity of order 3, 3 by 3, that's what you see there. Okay, so moving on, we're going to let A be an n by n matrix. That means that is a square matrix. And if there exists another matrix so please copy that definition. Let's let A be an n by n matrix. If there exists another n by n matrix, A inverse, we do not say A to the power -1, we call it A inverse, such that the product of the original matrix times its own inverse, you get identity. And since multiplication is non-commutative, write it over here. We must show both. That's why I have it written once. That either way, if you multiply, you will get identity. That's how you prove that two matrices are inverses of each other. Just like with numbers, like number 4 times 1/4 is 4 over 4, which is 1. So that's how you prove if a matrix is the inverse of the other. So we're going to do that for this example 1. So you guys on this side of the room, you guys multiply A times B. And then you guys on this side, you guys will multiply B times A. Okay, so we proved that that is the identity matrix. So here, 6 minus 5, that will be 1. 15 minus 15, 0. 2 minus 2, 0. And 6 minus 5, 1. So yes, we could say with confidence that those two are inverses of each other. Okay, now by definition, the way that we will find this is the following way. So if we have a matrix here, I'm going to take it from here, 2, 1, 5, 3. The inverse, let's say I don't know what it is, so I'm just going to use the letters W, X, Y, Z. And if I multiply a matrix times its inverse from here, what is it going to give me? What? I just circled that.
Identity.
Identity. So that is going to be, what is the identity for a 2 by 2? 1, 0, 1. Oh. Okay. And so if I was to create a system of equations, you guys are not going to have to find them this way. I'm just explaining it to you. I'm going to multiply first row, first column, so that will be 2W plus 1Y. And then I multiply first row times second column, so that will be 2X plus Z. Then I move on to this one here. So that's going to be
5W plus 3Y.
Thank you. And the other one will be
5X plus
5X plus 3Z, right? Okay, now based on the location or the address of those entries, this product here
you'd replace it with the numbers, right?
0, 1, yes. So that equation will equal to 1. This equation will equal to what number?
0.
0. And then the other equation right here, 2x plus z equals 0. And then 5x plus 3z is equal to 1. And so you see there are two systems, 2 by 2. We're not going to solve them because you guys are past that. But I can tell you that the solution for this was W is equal to 3. X is equal to -1. Y is equal to -5. And Z is equal to 2. So if we wanted to just write down the inverse, A inverse will just be the numbers that I wrote down there. 3, -5, -1, and 2. So imagine how complicated it will be to find it if it was like a 3 by 3 system. We will have a total of 9 equations. So we will have 3 systems of 3 equations each. So there are formulas and shortcuts to find inverses besides the calculator, of course. Okay, so that is the shortcut to find, the quick method, I should say, to find the inverse, multiplicative inverse of a 2 by 2 matrix. We're going to do the example in a minute. And it's actually very simple, but before that, let's complete the fill in the blank on the top of the slide. So I already mentioned that only square matrices have identity. matrix. Also, only square matrices have an inverse. Only square matrices, okay? You cannot find the inverse of a matrix that is not square. So that's why here we only refer to square matrices, okay? So if a square matrix has an inverse, that inverse is unique. That means that no two matrices have the same inverse. Every matrix has its own inverse, own unique inverse, only one inverse, kind of like a function. Now, if a square matrix has a multiplicative inverse, the matrix is said to be invertible or non-singular. And if a square matrix has no multiplicative inverse, then we call it singular. Okay. So what would that mean if we were using matrices to solve a system of equations? So if you have a matrix that is not invertible, then there is no way that you can solve the system of equations. And that could be that the system has no solution. And that's why. All right? So to find the inverse of a matrix, there's one thing that we need to cover first, and that is called the determinant. So let's look at the formula first, and then we'll get to what is the determinant in a minute. Okay, so if you guys look at the formula here, you notice here for the entries A and D, they're going to switch places. So let's write it down. So elements A and D switch places. And then elements B and C they will change to its opposite sign. Not that they will swap, change signs. They would just, for example, you guys will see in a minute. And then the last one is that you need to multiply by the reciprocal of the determinant. Okay, so what is the determinant? So let me show you quickly. So the determinant, we use DET to abbreviate that. You could also find it on your calculator. And the general form for that is that you multiply AD minus BC. So to find the determinant of that one, it's going to be -1 times 4 minus 3 times -2, like crisscross multiplication. So this is -4 plus 6, so that is 2. That is the determinant. Now, why do we care about the determinant? Well, if the determinant, okay, so first of all here, the matrix A is invertible if and only if the determinant is not equal to 0. Why? If the determinant was equal to 0, and we put a 0 here, 1 over 0, well, we get the reciprocal, what will happen? We can't, right? 1 over 0 is undefined, so you cannot multiply that by something undefined. So then we say that if the determinant is 0, right here, if the determinant is 0, then A is non-invertible. And therefore it is singular. And that leads to a system with no solution. Write that down in parentheses. System of equations with no solution. Yeah. So that's what it means. If you were to have a determinant equaling 0, then there's not even a reason for you to find the inverse. You would just say simply the inverse doesn't exist. Yes. Stretching? Yeah. All right, so let's just solve the problem here because the question was find the multiplicative inverse, not just the determinant. So we're going to have to use the formula that you guys see up here. So we need to have, for A inverse, we need the reciprocal of the determinant. And then we multiply times A and D switch places, B and C change to opposite signs. So let's do that. So A inverse is going to be 1 over what? What number?
2. Okay.
So that number comes from here, guys. And then not Andrew. What are the numbers that will go on the first row?
Which Andrew?
4 and 2. Very good, Julio. Very good. And second row. Not Andrew or Julio. What? So what happens with this 2? You change them to the opposite sign. So the 3 will become -3. And then what happened with the -1 and 4? They switch places. So the -1 goes here. Is it still negative?
Yes.
Yes, you do not change the signs for those. So then we multiply like a scalar multiplication. So 1/2 times 4, 4 halves. 2 times 1/2, 2 halves. 1/2 times -3, -3 halves. 1/2 times -1, -1/2. So then here we're going to have 2, 1, -3 halves, -1/2, and that's it. So that will be the inverse of it. Now, when you have a 2 by 2, of course, it's simple. I'm not even going to go there and scare you. But if we had a 3 by 3, we could also find it, but there's no shortcut for it. What we have to do is we start with something that looks like that, and then we do a series of row operations like what we did in 8.1 to convert it into something that looks like that. So we're going to do that in the next 5 minutes. So to find the multiplicative inverse of that, we have the following. 1 is 0, -2, -1, -2, -3, 1, 1, 0. So you're going to draw a line in between, and then you're going to write the 3 by 3 identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. And we're going to do a lot of steps. You might want to cry. And at the end, this is what we want. We want the identity to be on the other side. 1, 0, 0, 0, 1, 0, 0, 0, 1. And since we're not going to have time to finish, I'm just going to tell you what the answer is. Well, I'll tell you in a minute. Anyways, so the first thing we're going to do, you already know we have to work by columns, right? First column needs to be 1, 0, 0. Do we already have a 1 starting there?
Yes.
Okay. And then we already have a 0, right? So you start feeling a little lucky, like, oh yeah, this is not as hard, I can do it. Okay, so our leading row is going to be which one? Very good, Matthew. So that's leading row is R1. So we're going to multiply R1 times something to turn this 2, negative 2, into a 0. What is that?
So
Positive 2. And then we're going to add it to row 3. So we're not doing anything to the first 2 rows, just copy them horizontally. Okay, so you guys ready? Yes? Okay. So 2 times 1, that is 2. Minus 2, 0. 2 times negative 1 is negative 2. Minus 3, negative 5. And then 2 times 1, 2. Plus 0, 2. 2 times 1, 2. Plus 0, 2. Okay. 2 times 0, 0. Plus 0, 0. 2 times 0, 0. Plus 1, 1. Okay, so we're done with the first column. No crying yet. Now we move to the second column. What's first? What do I have to accomplish here first?
You make the top one 0.
No.
What?
The 2? The negative 2 needs to be a
Oh,
1. So we're going to say R2 times, what is the multiplicative inverse?
2.
No.
1.
No.
1.
1/2, but negative. Because we want to have positive 1. That's why we need negative times a negative. Okay. So let's multiply our second row. So 0 times negative 1/2 is still 0. Negative 2 times negative 1/2 is 1. 1 times negative 1/2, negative 1/2. 0 times negative 1/2, 0. 1 times negative 1/2, negative 1/2. And then negative 1/2 times 0 is 0. I'm going to copy my first and third row. Okay, next. We have the 1. What do we need to do? Now our leading row is R2. Yep. Because that's the one with the leading 1. Okay? Okay, so R2, we need to make this negative 1 a 0. So we're going to need R2 times 1 and add it to row 1. Okay. Or in other words, we're just adding row 2 plus a row 1. First of all, let's copy row 2. Do that, get it out of the way. Okay. Now right here. 1 plus 0? No. 1. Negative 1 plus 1?
0.
0. Okay. 1 minus 1/2?
3 over 2.
No.
1/2.
1/2.
Yeah. Oh, wait. No.
No, 1 is negative. Okay. 1 plus 0.
Oh, because we're... Okay.
1 plus 0.
We were adding 1.
1.
0 plus negative 1/2.
Negative 1/2.
And then 0 plus 0. 0. Okay. Now, this 5 needs to become a 0. So we're going to use the leading row times positive 5 plus R3. Now, follow my fingers. 5 times 0?
0.
Plus 0?
0.
5 times 1?
5.
Minus 5?
0.
Okay. 5 times negative 1/2?
0.
Negative
2.5.
Negative 5 halves.
Oh.
And then
and then
plus 2. 2 is a total of 4 halves. So negative 1 half.
yeah.
Okay, and then 5 times 0,
0.
0. Plus 2, 5 times negative 1 half, negative half. Plus 0, well, just negative 5 halves. And then 5 times 0, plus 1, 1. Okay, we're almost there, I promise.
Well, it's
Let's just do we move to the third column. First thing to accomplish is making the 1. So what do I need to multiply R3 by?
by
Negative
negative 2.
Negative 2. So just quickly, 0, 0, 1,
Yes.
negative 4, negative 5, no, I'm sorry, positive 5, and negative 2. I'm letting Julio go because he has a college class. Okay, and we're pretty much done with the row on the bottom. What we will have to do now is R3, which we're not going to do. I'm going to let you go. It's R3, now it's the leading row. To make this positive 1 half into a 0, we will have to use the additive inverse, which is negative 1 half. And to make this negative 1 half be a 0, we will use the additive inverse, which is positive 1 half. And that's how we end up with the final result, which I'm going to write here for you. And that is, was this example 4? Yeah. Yes. So 3, negative 3, this is negative. And then we'll have a 1, negative 2, 2, and negative. And that's it. So I'll finish this on Friday, guys.
That's pretty easy.